You could have the intuition for calculus. Derivatives as slopes, instantaneous velocities, or, as we discussed in the previous video, instantaneous stretches. And integrals as areas under curves, or total distances traveled given known velocities. But intuition alone is not enough for us to compute the derivative and integral of a given function. For this, we would need a notation that captures this intuition and applies it to a concrete function, allowing us to actually compute the derivative and integral of that function. Before we begin to develop this notation, we must clearly state why derivatives and integrals are the central objects that we need to express when exploring infinitesimal calculus. Recall how in the previous video we discussed that infinitesimals are simply a mental picture of tiny non-zero values smaller than any real number, and that these values are meaningful only when considered in proportion to each other. The proportion of an infinitesimal at a point along the x component of a function to an infinitesimal at that point along the y component of the function is the instantaneous slope, or the derivative, of that function. We see therefore that the concept of the derivative is the natural object of study in infinitesimal calculus, because it gives the infinitesimals their meaning. You can review the previous video to see that integrals follow naturally from derivatives as well. So the first natural step to exploring calculus is to define notation for an operation that accepts a function and an x value and outputs the value of the derivative of the function at that x value. We want this operation to be such that if we replace the concrete x value with a variable x, we would find the function expression for the derivative. So in this video, we will introduce the notation for this operation, called the limit notation. This intuitive notation allows us to discover derivatives of functions. We will also look at the infamous Epsilon-delta definition of limits, which helps compute limits for certain classes of functions that are not easy to compute using the limit notation. Fortunately, our notion of limits has certain properties that allows us to construct limits for bulkier composite functions out of limits of simpler functions. These properties of general limits will be useful when computing derivatives of functions, since the derivative is computed using limit notation. We want this limit operation to allow us to find the ratio dy over dx of a specific function y of x at a specific value of x. There is nothing tricky about representing a slope between any 2 points along the curve of the function. This expression already contains the function y of x and the x values at both points. Our goal is to represent the instantaneous slope at one point, without losing information about the x-coordinate at that point, and about the function itself. We recall that differentials dy and dx are simply infinitesimal distances associated with the process of approach of the point x2 to the point x1, so we can capture this process with notation using limits. The arrow under the lim signifies that a process of approach is happening. In this case, the distance between the x-coordinates approaches 0. We still have two x values and no indication of which point they are both approaching, as the distance between them decreases. Without loss of generality, let us suppose that x2 is approaching x1. Now we don't need to include x2 in the expression at all, since x1 is the only point at which the derivative is being computed. So we represent x2 as x1 plus an ever-decreasing positive h, which is the difference between the two x values, and propagate this difference throughout the expression. There are still two variables here, but now there are two advantages gained. One, the computational benefit is that now we have x1 in both occurrences of the function y. So when we know a concrete function, we can expand the expression and further simplify it. Two, we can also now treat x1 as just a variable, and so get the general derivative function, rather than just the concrete value of the derivative function at a specific x value, and allow the limit notation to handle the h variable, as in this example. In practice, we oftentimes divide out the h and find the derivative. This is the power of the limit notation. Now in this slightly more complicated example, as h approaches 0, it simply disappears. This example actually highlights a very important intuition about limits. Plugging in 0 for h does not make sense before we simplified this expression, because division by 0 is not allowed. So we are not actually plugging 0 in for h. Rather, we are observing what happens to the value of the expression as the value of h approaches 0. This limit would be equivalent for both expressions. This is because both expressions have the same values for all x and h, except that the left expression is not defined at h equals 0. This makes sense because instantaneous slope is not possible due to the division by 0 problem. So it is only a limit approximation. Here's a demonstration of this concept of approach with simpler functions. The limit of the function y equals x as x approaches 0 is 0, because the value of the function approaches 0 as well. We can see that the limit of sine of x as x approaches 0 is 0, just by looking at the graph. Now what about the limit of sine of x over x as x approaches 0? From the graph, the function obviously approaches 1, but you know that sine of 0 divided by 0 is undefined. Well, this is not a problem, because the limit represents approach, not plugging in. So the limit is indeed 1. How do we know the values of limits for certain? We cannot simplify this expression by factoring out the x, as we factored out the h in the derivative examples. This is not a question for daydreams, because we can come across this situation as well when dealing with derivatives of certain functions. We can check this by using the infamous epsilon-delta definition of the limit. Before discussing this definition, keep in mind that this is not a replacement for limit notation. The limit notation will be very useful for us when we demonstrate general properties of limits that allow us to find limits of composite functions. Students are often afraid of this definition, and this is because it contains pitfalls. Let's talk through how we would construct a definition for the concept of the limit. We can begin by saying that for any point along the x-axis, no matter how close to x equals to a, the function will map it to another point very close to the limit L. So the limit is approached by the function as the x-coordinate approaches a in value. Since we are now not using limit notation, we can't represent the process of approaching with an arrow. So instead we identify closeness to a point by being at a distance of less than some arbitrarily small value delta from the point x equals to a, on either side of that point. Then we must have a tiny value of epsilon such that the corresponding distance between f of x and limit L is less than epsilon. But how do we specify how tiny this value of epsilon must be? We could define it to be directly proportional to delta, so as to ensure that as delta approaches 0, so does epsilon. This would also get rid of an unnecessary extra symbol, keeping only either epsilon or delta in the definition. What is wrong with this approach? Why can't we let epsilon be equal to delta, for instance, so that we would not have to worry about epsilon at all? The problem with this approach to the definition is that we do not know the slope of the function at x equals to a beforehand, since this is a general definition that is applicable to any function at any x value. So if the slope is, for instance, 5, then we will have a point in the neighborhood of x equals to a for which f of x will be up to 5 delta distance away from L. This problem can occur whenever we represent epsilon in terms of delta. So the approach of representing epsilon and delta in terms of each other is in fact a pitfall. Then let's set epsilon to a tiny value first. We know that epsilon is the value that must be decreasing towards 0 as the value of the function approaches the limit L. Are we required to constrain to delta? If we look at the function with a tiny slope, we see that this is not necessary. We only need to assert the existence of a delta, which ensures that any point at distance delta or smaller from x equals to a is mapped to a value no farther than epsilon from the limit, for any epsilon, no matter how small. No matter how much we compress the interval to delta, the resulting interval still satisfies the epsilon-delta definition. The delta is the upper bound of distances from x equals to a acceptable for a given epsilon value. This is the epsilon-delta definition of the limit. The trick to understand is that the epsilon, the distance to the limit, is required to decrease towards 0, and the delta value follows the decreasing epsilon. A possible source of confusion is that the definition does not force the value of delta to be arbitrarily small, but instead states the existence of at least one upper bound delta. with all smaller delta values also satisfying the definition. Here is the same definition, written down in standard mathematical notation. We swap the order of the last two statements to write down the causality relationship. If we began by setting delta to an arbitrarily small value, we could not also take any arbitrary epsilon, because not all epsilon-delta pairs work for the definition. We could then only claim that there exists a positive epsilon for any positive delta. But this would defeat the purpose of the definition, because in examples such as the one shown here, this definition satisfies functions at points that do not have limits. This function approaches different points from different sides at x equals to a, so it does not approach infinitesimally close to a specific value of the function. So there is no limit. We will stick to the original definition that we came up with, since it ensures approach towards a limit. Let's look at a simple example of using this definition. We can leave trickier examples for a separate video. For any positive epsilon, if we find at least one existing delta such that 2x minus 2 is less than epsilon whenever x minus 1 is less than delta, then we proved that the limit of this function at x equals to 1 is 2. We see that we can set delta equal to epsilon over 2, or anything smaller and positive, and the inequalities are always satisfied. Therefore, we can always find the delta for any epsilon, so the limit holds. Note that there is no contradiction between expressing epsilon as a function of delta and what I said earlier about how we should avoid doing this. Earlier, it was unsafe to assume any relationship between epsilon and delta in the general definition of the limit, because that would be an erroneous one-size-fits-all approach to functions. The general definition does not make any assumptions about the function and its slope at any point. Now, this relationship is an upper bound for a concrete function at a specific point. This definition would not work for an incorrect limit. We will explore why this is the case in a separate video with limit problems. We have introduced the concept of the limit and the representation of the derivative as a limit in order to present a convenient notation for discovering derivatives of given functions. Since the derivative is a limit, the properties of limits are applicable to derivatives, allowing us to compute derivatives of composite functions from the discovered derivatives of simpler functions. We will introduce ourselves to these properties in the next video. A subsequent portion of Calculus 1 is dedicated to discovering derivatives of the simpler functions, so we will worry about them later. We will also discuss the concept of continuity, a property of functions that we want to be aware of when exploring derivatives.